5% is 1.05. You just multiply, you just add 1 to it in the percentage. So 5% would be 0.05. So to increase something by 5%, you'd use 1.05 or equal. The 1.5 is for the VF of the diode, not for our LED. We talked about that. LEDs are not made out of silicone. Silicone gives us a voltage drop of about 0.7 of a volt. Diodes are made of different dopants of gallium, so they have a VF, and we don't use these things as diodes. We use them as lights, right? You understand? So this guy has a VF of around. The VF is usually around about 3.5 volts. It depends on what LED you got and what color it is and what they dope it with. So rule of thumb, we use 2 or 1 here. Rule of thumb, we usually use 2 volts. If we don't know, if I got the data sheet for the thing, I look up the VF. But you'll find out around 2 volts works out okay. But this, I give you the VF of the diode. That explain that, Brian? Yeah. Yeah. So R2, VR2, when we saturate it, it's going to have to drop 15 volts minus 1.5 volts. So what does that give us? Oh, okay. So 15 volts minus 1.5 gives us what? And then now I know, so I can calculate R2. R2 is equal to V 13.5 over I, which is 15 milli. So what does that give us? What's that? Exactly? Okay, what'd you get? Now, what'd you get in your answer? What on my sheet did? Of course, here we rounded up, right? So what we're going to do, these guys, is we're just going to round them. We're not going to round up. We're not going to round down. We're just going to round them, right? Yeah, just the nearest standard value. We're using minimum beta. So odds are, it's never going to be minimum beta, right? No, we got 900 as the answer, and we just rounded it to 910. So the next standard value, nearest standard value. I'm sorry, I didn't say that, but that's what I meant. So we round it to the nearest standard value. The sheet that we gave y'all. Yeah. What's that? Yeah, but it's on Blackboard too. It's in the handout section, by the way. In the reference section. Which also has a sheet that shows you all those symbols that y'all are supposed to study for the test, right? So what I'm going to do is I'm going to calculate IB SAT, what we call IB saturation current. This is calculated. What I'm going to do is I'm going to take my 15 milliamps. 15, I don't know where I got 50, guys. I'm going to take my 15 milli and I'm going to divide it by 75, minimum beta, right? And this gives us our saturated base current. Now the base current we're going to round down. The collector on a saturated switch, we just round, right? I mean, we go to the next value. I'm not. So 15 milli divided by 75 gives us what? $200 microamps. So R1 is going to equal to 5 volts divided by 200 microamps, and we will round this one down. Uh, 2.5K. Oh, 25K. And that's rounded down from what you calculated. So we know we can operate a transistor in 3 different regions. What's the 3 different regions? Yeah, active. Yeah, this is what we're doing here, right? Saturation. And then cutoff. This is what we're doing here, right? That's a T. And then in active region. So what we're doing is we don't operate them always saturated. We don't operate them always cut off. So when we use it as a switch, what we're doing is we're switching it between saturation and cutoff. How can we tell it's saturated? Not the amperage, volts, but what voltage? If it's saturated, what voltage should a transistor drop if it's saturated? And we call that, this is a very important voltage measurement. We call it voltage collector to emitter. So that means this tells you where you put your common on your meter. This tells you where you put your red lead on your meter. So it means I would come over here, I'd put my black lead right there. I would put my red lead right there. And this would tell me if the transistor is saturated or not. So when do we say the transistor saturated? Yeah, if it drops less than a volt. When voltage collector to emitter, when do we say it's cut off? 1 volt, Rich. Well, it will drop all. Our meters can't measure. When this sucker's cut off, there is a leakage path through there. I think when we look at the data sheet for the 3904, it's like 50 nanoamps. So we don't have a meter that has the ability to measure that. So it's going to be equal. I'm going to say approximately, but it's going to be equal to approximately VCC, whatever this voltage is right here, right? And when it's active, when we say it's active, yeah, it's in between that. Yeah, between 1 and VCC, we say it's operating in active region. Now, what we try to do is we try to put it right in the center, and we'll show you all that when we bias it, and we'll show you all the reason why. So when we saturate this thing, if we put that 910, I'm sorry, if we put that 25K right there, we put 5 volts in. This guy right here is going to put enough base current. It's going to cause this resistor right here to drop whatever the diode don't drop. It's going to drop 13.5 volts. This guy's dropping 1.5 volts. What's left over from the transistor? Looks like none, but it's going to be something, but it's going to be less than a volt, right? You understand that? Here you go, Walter. So we call this DCE. That stands for voltage measured between the collector and the emitter. This is a very important voltage measurement because this tells us what region the transistor is operating in. Good. So less than a volt, we assume it's saturated. More than if it's dropping DCC, cut off. If it's somewhere in between, we say it's in the active region. So what else? Was that all we need to do on that one? Was that the calculations for everything? What's that? Yeah, VR2 we calculated right here. Yeah, so what we do is we start on this side and we work toward the base, right? Understand that? So even, are we okay? Are we okay? Yes, no? What do you mean? For the diode? Yeah, that would be the actual data but vote. It's somewhere between like 1.5 to 3.8, right around in there. So if you don't have the data sheet, 2 is a good number, right? 2 is a good number. Rule of thumb. Yeah, approximately 2. We wouldn't say 2, we'd say approximately 2. And that's the way it would be on a test. So what we could do, and I don't know if I've got that data sheet up there. I need to bring it up, but we've got a generic data sheet that shows you the colors, shows you what they're doped with, and it gives you the basic VF of the diode. I'll make sure it's up there because that way you don't even need the data sheet. You can just look at the color. By the way, the lens enhances the color. The color of the LED is determined how it's doped. This is why you can see a clear lens LED and it might be glowing red. It's just not going to appear as bright as one with a red lens on it. Does that make sense? Sure. As soon as I find it. Where it is. Yeah, because I can draw on PowerPoint. So I'm cutting off the worksheet and paste it into PowerPoint. So we know this guy right here is 12 volts, 150 milliwatts. So I'll call this the lamp. Would equal to, so here's our formula. We got to know I, but I know P is equal to what? Huh. No, somehow it lost the. I had to read it. I had to disconnect it and reconnect it so it would discover it again. So I know power is equal. I need current. I got this information right there, and I need current. So I know power is equal to V times I. So what would I be equal to? It would be equal to P over V, right? So I'd say 150 milli divided by 12, and this would give me the current required by my light. Well, it is the load. This is the load right here. This is the load. Now, where'd you get R of the load? You're looking at what? What we're trying to do is we're trying to solve for IC saturation. Okay, but the problem is that we're given two things. So normally in electricity, if I have two things, I can always solve for the third. Okay. So what we're doing here is I know the voltage and I know the watts, right? Y'all understand? Now this formula probably wasn't given because this is one of the formulas you should what? Already know. If you know power and you know voltage, you can solve for the current that's required to provide that power, right? That makes sense, Brian? Okay. So what do we come up and get right here? So everybody okay? And this is what light bulbs are usually rated at. So my house, we don't see them much anymore. But what are light bulbs you put in your house? What are they rated at? They're rated in wattage and they're rated at a voltage, right? You understand that? But you could calculate the current that thing pulls when you turn it on just by taking what? Watts over watt over volts. And you could calculate the actual current, which you'd need to know if you're going to hook a bunch of lights up to a circuit, right? Okay, now I've got IC sat. It's 12.5 milliamps. So IB saturation, we would take 12.5 milli and we divide that by 50 because we're using minimum beta, right? Everybody okay there? Then I would say R1 would be equal to 11.3 volts divided by 250 micro. So we're definitely going to have to choose the standard value on that, right? Is there a 45.2K? Yeah, we use a 43. But this is what's so neat. You understand we're using about 245 microamps of base current to control 12.5 milliamps of collector current. So this is what we get on transistors. We get an extremely high current gain. Of course, if we can get a current gain, we can get a power gain, right? You understand that? And of course, that's the ultimate goal, is to get power gains out of these transistors. Why? Because power is work, right? That's how much work we're getting out of the circuit. So we can get a lot of power gain. I mean, we can calculate the power gain with this transistor, this resistor right here. We're using a 43K. So power N would be equal to 11.3 squared, right, divided by 43K, V squared over R. So what's our power N at? Yeah, that's one of our power formulas. It's easier to use that. But now we do know current, but we calculated current for this resistor right here. We didn't calculate current for that resistor right there. But that's okay. We don't need to, because we know one of our power formulas, right? So what's our three main power formulas? Power is equal to V times I, which we use all the time. And then we got power is equal to I square R. And then we got power is equal to V squared over R. That's our three main power formulas. What's that? So what's our input? What's our power in? 11. What's that? What's that? What's our power out? Our power out, we're given the power out, right? You understand that? So power gain, by the way, in electronics we use A to represent gain. Then we put what gain we have out there, so that would be AP. Anytime I calculate gain, it's out. 150 milli over 2.9 milli. So what would my power gain be? So anytime we calculate gain, it's out over N. 52. And what unit is that? It don't have a unit, it's gain, right? So if I know the power gain, I know how much watts I put in, I would multiply 52, and that would give me the watts out. Now, so I take the log of 52, common log of 52. Anybody got that on their calculator? What's that? Or this would have, and what I would do is I'm going to multiply this by 10, and what I get when I multiply that by 10. So this thing here would have a 17 dB gain. So all you do to calculate dB is you take the common log and you multiply it by what? 10. And that's what dB is. So dB is just a technical term we use for gains. Have you ever heard the term dB? Now you know what it is. So what would, if I seen 17 dB, what would the gain would be? Well, I would just move the decimal point to the left, and I would raise 10 to the 1.7 power, and that would tell me the actual gain. So we use dB kind of like we use engineer notation. It allows us to round. So we round in dB. We'll round usually no more than one decimal point, and we'll round it once we convert it to dB. So it's not extremely accurate, but it's accurate enough. So that thing's got a 17 dB gain right there. Have you ever heard the term dB? If you've been in audio, I guarantee you've heard about dB. If you talk about hearing, our hearing hears in a logarithmic scale. So that's originally where dB came up with, but now we use it for gains, we use it for attenuations. So. Okay, everybody okay so far? So by the we got a roof leaking next door, so I hope that's what they're doing out there when it rains. Yeah, over in 107. So here we have a relay. So what's the purpose of the diode? What's the purpose of diode? It's in the reverse bias. We went over the lab last class. We put an inductor out there. We charged that sucker up to 12 volts. When we disconnected, that thing discharged over 90 volts. It would blow its transistor out. So what happens is when we charge the thing, we come up here, we put plus 12 volts there. Is the diode forward biased or reverse biased? It's reverse biased. So all my current flows through the relay. When we turn the transistor off, this thing discharges, but when it discharges, this goes minus. That's why it's called a counter EMF. This goes minus, this goes plus. That's forward bias to diode, and it discharges that it lets that inductor discharge without going through my transistor. Right? You understand? If you don't have that, I guarantee you, it's going to blow your transistor out after a while. So that's a count. We refer to that. Some people call them flyback diodes. I learned it. It's a counter EMF, which is always opposite of the voltage you apply. So here we're given two things. So I need to calculate my saturated current. This guy needs 6 volts at 750 ohms. So relays are usually rated in ohms. So I know two things about the relay. I know the voltage that's required to run it. I know the current that's required. I know the ohms that it has. So IC sat, saturated current is got to be, what's the formula for I? No, 6 over 375 ohms. So I know VR1 has got to drop how many volts? It's got to drop 6 volts over 16 milli. So if you had a relay and you knew it was a 12 volt relay, but it didn't give the ohms, what would you do? If you had a relay and you knew it was a 6 volt relay and it didn't give you the ohms, what would you do? Well, you didn't know the ohms. You didn't know the ohms. You don't know the current. All you know is that it's a 6 volt relay. I got plenty of information. I would take my ohm meter. I would get that relay out right here, and I would take my ohm meter, I would put it across that sucker, and I would measure the watt. I'd measure the ohms, right? Okay. So here we give you the ohms, but you'll see this all the time. You say, "Well, I got like your car. You got your car. It's a 12-volt relay. It may or may not have the ohms on it, right? You understand? And all you need to do is just use your ohm meter, and you can actually find the coil. If you don't know where the coil's at, you can actually start moving around the pins because your contacts are either going to be normally open or normally closed, right? So a contact is going to either measure infinity or it's going to measure almost zero ohms. And when you find ohms, then you found the what? You found the coil. So VR1, what's VR1 going to be equal to? 375 ohms? Is that a standard value? Here we're just going to round this guy. We'll round it to the nearest one. If you put a little too much current in it, it's not going to hurt it. If you put not enough, it's not going to hurt it. So what's our closest ohm value to that guy? Oh, so my saturated base current. We've already got it. Got it right there. Well, what we did, this is the load. This is the true load, but the problem is I'm putting 12 volts across a 6-volt relay. What would happen? The relay is going to burn up because the relay would be trying to produce twice the power, not twice, 4 times the power. Y'all know power varies with the square, right? You understand that? Because if you double the voltage, according to Ohm's law, voltage and current are directly proportional to each other, right? You understand? So if you double the voltage, the current doubles, and what's power equal to? V times I. So power varies with the square. So what would happen, this relay, I would make that coil produce 4 times the power than it's supposed to produce. So what would probably happen? It'd burn it up. So what we do is we say, okay, I can do this. I need something to get 6 volts across the coil. I need something that drops a voltage with a current. What drops a voltage with a current? A resistor. So I put another resistor in series with it to drop the rest of the voltage. We was working over, we had a 26 volt coil. And the only thing we had over in the motor control lab was 120 volts. How can I run a 26 volt coil on 120 volts? I couldn't. But what did I do? I put a resistor in series with it. Worked fine, right? So, so I'm trying to teach y'all. A lot of times we have a load that don't match our power supply, but we've only got one power supply. And we do this all the time. We call them voltage dividers. What does a voltage divider do for us? It gives us it splits the voltage up. So we do this all the time. Instead of me having 15 power supplies inside a computer, I've got what? Maybe 2. And how do they get the other voltages? They just use what? Resistors or voltage regulators. So actually, this one I don't know. Standard standard desktops, we have a plus and minus 12. We have a plus 5. And now we have a plus 3.3, by the way. We're not there for R2 yet. We're dealing with the base. We're fixing to go there. Yeah. So ICSAT we're dealing with this circuit over here. So what we did is we took what we knew, and we knew it was a series circuit, right? You understand? We knew the transistor was dropping approximately 0 volts. So for all practical purposes, even though it's not going to drop 0, we're going to use 0, right? And why can we use 0? Because all these are everything inside this is within tolerances anyway, right? Does that make sense? So what we did is we used this guy to calculate the saturated current because this is the true load, but we knew we had to drop what? We had what up here? 12. We knew we had to drop 6 volts right there, according to Kirchhoff's voltage law, right? So we're setting up a voltage divider, guys. So how do I calculate IB sat? Well, I'm going to take this 16 milliamps and I'm going to divide it by minimum beta. And what do we get for that? And then R2 is going to be equal to 4.3 volts divided by 333 micro. And we'll round this guy down. So what laws are we doing? I mean, where did you learn all these formulas? Or are you supposed to learn them? DC, except for one. What was that? Beta. That's a new formula. Yeah, I know. And I don't know. What to do about that. But if you really understand these basic laws, if you really understood them, then a lot of this would make a lot of sense. But yeah, R1 was what? Yeah, I've done I've done erased it. Now, so what we give you is I give you the voltage at this point right here. So the other day we just made up one, right? When we worked this basically this same circuit. What here I gave you what voltage we wanted right there. So what do we want right there? 3 volts. Okay, so we can calculate IC sat. What's IC sat? Yeah, 12 divided by 1K. Good. That would be 12 milliamps, right? And then I can calculate IB sat. Yeah, 12 milli divided by 50. Now that we can calculate VR2, so we got to go a little way here. So what's VR2 got to drop? Good. 2.3 divided by, so y'all worked the hard one? 240 micro. Great, guys. Nine point one K. So VR1 is going to equal what? That would be the size. VR1 though would be what? It's going to be 12 minus 3, right? That gives us what? 9. Minus 3 because it's Kirchhoff's law, right? And you don't have to take out the 7/10 because that's by this resistor right there, right? Understand? So when we came up here and we measured that, that's going to measure 3 volts. So we know that guy's got to measure what? It's got to measure 9. Yeah. Yeah. Now we can calculate R1, and this is going to be approximately, guys. So what would R1 be? Yeah, but actually it wouldn't be 240, and that's why. It'd be a little more because to get extremely accurate, but we're going to round anyway, because that 240 was what we'd get if we used a 9.6K, but we didn't use the 9.6K, we used a what? 9.1. So to get the actual saturated base current, I would actually have to recalculate that, but this is okay. I mean, it's going to be close enough anyway. So that's good. 9 divided by 240 micro would be a what? That's standard value? It is. Now I got to calculate IC sat for Q. Oh, I didn't put a Q numbers on here. Is it on y'all's? Q numbers. Didn't I call this Q1, Q2? I need to put that on the. Okay. So IC sat for Q1 is going to be what? And how'd you come up and get that? When we saturate it, R1's going. So the way this works, guys, is that when this guy here saturates, we get 0 volts right there. So what would Q2 do? Would it be on or would it be off? So I've got 0 volts on the base of Q2. Would Q2 be on or off? Off, yeah. So the way this works, when Q1 is off, Q2 is on. When Q1 is on, Q2 is off. So when we saturate it, this guy here's got to drop all the voltage. We chose the what? We chose this guy right here. So it's going to be 12 divided by 37.5K, if that's a standard value. Because when this guy saturates, it drops all the voltage. This resistor that we chose drops all the voltage. Right? You understand? Because it's a saturated transistor. And that's what gets people confused because they want to go to 3. But when we saturate it, what do we say this thing drops? We say it acts like a closed switch. It drops 0 volts. So what I end up with is I end up with this circuit right here. And this is R2. Well, if I close that switch, that takes that common and puts it right there. Right? You understand? So that means we have approximately 0 volts right there. Right? You understand? To get this circuit right here to work, what do we have to have? We got to have at least what right there? We've got to have at least 7/10, actually more, because 7/10 of a volt would try to conduct, but then this guy here would drop it below 7/10 of a volt, so we'd still be cut off. So if we bring this common right here, that means this guy right here, if I put plus 12 volts right there, then now this guy is no longer dropping 9 volts. It's dropping what? It's dropping the entire thing. So what would IC sat be for Q1? Yeah. And we're gonna get a lot of gain out of this one. Then IB sat would be equal 320 micro divided by 50 divided on this transistor. .4 microamps. So it's taking 6.5 microamps to run this circuit. We're getting 20 milliamps out. Well, that's a pretty good gain, right? How many dB would that be? No, you'd have to get it to power first. We could get the current gain. We got a big current gain. So gain, we use it A. No, yeah, no, it's not on test. So A, we're calculating current gain, so we'd put a little I right there. And what's my output current? 12 milli divided by 6.4 micro. So we got a current gain of that has no unit. No, that's not 18,000. So every transistor gives you a current gain, right? You understand? So this, oh, we hadn't calculated yet. Thank you. R4 would be equal to 11.3 divided by 6.4 micro. This is going to be a big O. Is 1.6 meg, is that a standard value? What's the standard value? No, we'll go down. On the base, we go down. So there's nothing between a 1.6 and a 1? Okay. I believe you. I mean, I just thought there were. Oh, you don't have your standard resistors? Okay. Well, we don't know this one. Yeah, I thought y'all carried that around in your wallet. Whip that thing out. Whip that thing out. That's one chart I don't have memorized, guys. So this is not going to be a test. But what we're doing, of course, on these worksheets is we're just trying to get you to what? Figure out what you should already know. So everything we do here is what you should what? Already know, yeah. So that's worksheet. We got questions. So no, one of these won't be on test. Why? Just one. A saturated switch is on there. But y'all know how to identify saturation, right? What do we use? What measurement do we use to identify saturation? That voltage what? Collector emitter. If it's less than a volt, we assume it's saturated. If it's equal to what we call VCC, which is the whatever you put up on the collector up there, we say it's cut off. If it's between 1 and VCC, we say it's in active region, which is where your amplifiers work at. Your power amplifiers usually work in, and we go through stages. So how many volts do you think you're getting off that little antenna you have in your car or on your cell phone? None. So you know we got to go through a lot of different gains, right? You understand that? We start off low. We start off with low gains, and we'll talk about it later, and we end up with real high gains on the end. So about 6 stages of amplification is usually what we go through to get it from almost nothing to something we can use. Are we okay? All right, guys, y'all take a break, and we'll come back, and we're going to do a lab. What? And we'll let y'all do. Y'all gonna do this lab. I'm not gonna do it in class. And